Hello everyone, this is Matheus Rosa. I'm a PhD student at the University of Colorado Boulder, working with Professor Massimo Rosini. Today I'll talk about our work on amplitude-dependent edge states and discrete breathers in nonlinear modulated lattices. This work was also done in collaboration with Dr. Michael Leamy from the Georgia Institute of Technology. So recently there has been some interest in exploring the role of nonlinearities on topological modes. Topological modes are originally defined for linear systems, and they have vibration modes whose frequencies are inside a bandgap. And these modes have vibrations localized at an interface or at an edge of a structure. They are supposed to be robust against defects and imperfections due to the properties of the topologies of the band. Now, some works try to explore what happens when nonlinearities are introduced in the systems. These are a couple of examples of papers in this field. The first one explores interface modes on a dimerized one-dimensional chain implemented using magnetic spinors. In this case, the authors have shown that the frequency of the interface mode exits the region of the linear gap as a function of amplitude. And when it exits the linear gap, the degree of localization of the mode, as you can see in this figure here, decreases. So essentially, with increasing amplitudes in the nonlinear regime, the topological mode can become less localized. In this other paper, the authors have shown that by intercalating nonlinear stiffening and softening springs, you can find a transition, again as a function of amplitude, from a trivial gap to a non-trivial gap. So an underlying theme in these works and other works in this area has been to explore the behavior of the systems as a function of amplitude and what interesting transitions can be found. In the current work, instead of looking at dimerized one-dimensional chains, we will take a look at modulated elastic lattices. So we consider a one-dimensional spring mass chain, and we modulate the stiffnesses of the springs according to this law here. It's essentially a cosine modulation of the stiffnesses of the spring constants, which has a DC term, an amplitude, and two important parameters that are highlighted here. The frequency of this modulation will determine if the system is periodic or quasi-periodic, and variations of the phase of the modulation will reveal the existence of topological edge states, which I'll talk about in a minute. And in nonlinearities are introduced in the system in a cubic form, such that the force exerted on a spring is given by this expression here. So this is the equation of motion that one would get for one of the masses on this chain. As you can see, we find the nonlinear cubic stiffness terms in this part of the equation, and then this is a regular linear kernel. So I'm not going to go into too much detail on how we solve this equation. We essentially use two different approaches that are well defined in the literature. For finite systems, we apply a harmonic balance method, both in terms of a modal analysis and also for forced response computations. And for the unit cell dispersion, we use a multiple time scales method. So these methods can be found in a variety of papers. Two of them are cited here, and there are many more references therein. As a starting point, we will take a look at what happens in the linear regime first. Throughout this presentation, I will use the theta parameter to be equal to 1/3, and this causes the lattice to be periodic, in particular with a unit cell containing three different spring constant values that repeat in space. In this figure, we show the eigenfrequencies of a finite lattice with 42 masses as a function of the phase parameter that are displayed with black lines. The shaded gray regions correspond to the limits of the block bands obtained on the unit cell, also as a function of the phase parameter. And we can see that there are two additional modes spanning the two band gaps as a function of the phase parameter, and these are the topological edge states. One example is highlighted for a particular phase value of 0.35, where you have the modes displayed on the right panel. The first mode inside the first gap is an edge mode localized at the left boundary of the chain, and the second mode is a regular bulk mode on the second band. The third mode on the second gap is an edge mode localized at right boundary instead. And these modes can be predicted based on the Chern numbers that are given here, and more details about the computation and the topology can be found in our paper referenced below. So to look at the nonlinear behavior, we fix this particular phase value here, where we have the linear modes of the system. And using a harmonic balance approach, with the linear solution as a starting guess, we investigate what happens with these modes as a function of amplitude. The results are displayed on this figure, where we plot the variations of the frequencies of the modes as a function of amplitude. The amplitude is enforced as the norm of the displacements along the chain, whereas for very low norm values, for very low amplitudes, we have the linear solution described in the previous slide. The shaded gray regions denote the regions, the limits of the block bands obtained through the multiple time scales method. In general, we can see that as a function of amplitude, the bulk modes remain inside the regions determined by the bulk bands, but some additional modes detach from the bulk bands as a function of amplitude, and the edge modes may also converge and remain tangential to the bulk bands. So let's take a look first at what happens with the edge state in the first gap. We plot here the mode shape of the solution for these dots highlighted in the branch. And we can see that since this mode remains inside the gap, the edge mode for this case remains concentrated very strongly on the left boundary. So there is no big change in the mode shape of the edge state for this case. For the second edge state, however, we observe that as the amplitude increases, it converges and becomes tangential to the bulk band. As it does so, it becomes less localized, as displayed on the figure on the right. So at this point, I would like to point out a recent work by Vakakis and co-workers, where similar observations have been reported for interface modes. So instead of modulated lattices, this is a dimerized lattice with a mode localized at an interface. And they also reported that the frequency of the interface mode as a function of amplitude becomes tangential to the region of the nonlinear bands, and as it comes closer to the bulk band, it loses a certain degree of its localization, as illustrated in this figure. In addition to the edge states, we can see that some modes detach from the bulk bands, and one example is highlighted in this figure, where it becomes a discrete breather localized at the center of the system. This behavior has also been reported in the past for simple monatomic lattices, where the authors have described that discrete breathers may occur as instabilities of the band edge plane waves. So essentially, these modes that are on the edges of the bands, they detach from the bulk bands and become discrete breathers. And as an illustration here, I computed the frequencies of a simple monoatomic lattice with cubic nearest neighbors nonlinear springs. And as a function of amplitude, we can see that this mode, which begins as a global mode, becomes a discrete breather as it detaches from the bulk bands. We can also take a look at a few other modes that detach from the bulk bands. In this example here, it becomes localized in two independent regions as it detaches. And in this example, it becomes localized at three independent regions as it detaches. And you can find more examples with 4 regions and so on. We can also find these breathers for the other bands. For example, in the second band, this mode detaches from the band and enters the region of the band gap. And as it does so, it becomes localized in the interior. After observing the nature of these modes, we do a few forced response computations to confirm the amplitude-dependent behavior. We start by illustrating the force response in the linear regime, where we have a finite chain, and we apply a force on the right boundary. So on this figure, we show how this force excites the right localized edge state. On the x-axis, we have the length of the chain, and on the y-axis, we have the frequency inside the second gap we see the right localized edge state. So this is how the response at the right edge as a function of frequency would look, with this peak corresponding to the edge mode. The forced response in the nonlinear regime is computed also using the harmonic balance method, and the results are summarized in this figure. The blue curves are the forced response in the linear regime for increasing force values, while the red curves concentrated on the region of the edge mode are the force response in the nonlinear regime. You can see the stiffening behavior of the edge mode as illustrated also in this zoom on the right. In particular, the black dashed line corresponds to the amplitude of the mass on the right edge as a function of frequency obtained in the modal analysis of the previous slides, and it confirms that the veering of the forced response curves follow the backbone given by the curve of the modal analysis. Here we take a look at the responses at the peaks, which are marked by little red dots, and we can see that their shapes as a function of amplitude starts to become less localized. In the future, we wish to increase the forcing even further to see the complete transition along the backbone curve, but for now we have been dealing with some issues in the numerical solution. So to summarize, we have shown that the nonlinearities produce a series of transitions with amplitude, which may include the reduction in the degree of localization of an edge mode, or the emergence of discrete breathers as the modes detach from the bulk bands. In particular, this can be interesting to induce amplitude-dependent transitions of localization. For example, if we take a look in the region of the second gap here, for a fixed frequency, we define an edge mode localized at the right boundary at low amplitudes. However, for higher amplitudes, instead, the edge mode is on the bulk band, and we identify a discrete breather which is localized in the interior. So one could induce a transition at this fixed frequency by increasing the amplitude and going from right localization to localization in the interior of the domain. Finally, I would like to thank our supporting agencies and both my advisor Dr. Rosini and Dr. Limi for the collaboration on this work, and thank you for listening.